Good morning, everyone. So today I'm Xiaobing Hu from our Nirvana Center from EPIC. So today I will talk about something about the space group tables and how to use them for your electron diffraction pattern indexing. And in the bottom one, you will find my contact information, my email, my office address, my phone. So if you want to discuss or if you need some help, you can contact me directly. And also during my talk, if you have any question, you can put it in the chat. Then I will address when I saw them. So now we can begin. So this is the outline of my talk today. First, how to index the electron diffraction pattern. And the second one, I will give an introduction about the lattice point group and the space group. And then I will show you the contribution of the unit cell, their contribution to the intensity of the diffraction. The first one, I will show you how to use space group table. So I basically refer the book. If you want to read more details, you can check this book. It's an international table for crystallography. So it's A. I mean, there is some other book, B, a CD. There are four. So I use A. Okay. So how to index different patterns? You need to consider actually many things. So honestly speaking, I mean, in many publications, I mean, their electron diffraction index, I mean, it's wrong. So although their work were published. So, in order when you index the reflection, you need to consider many things. For example, the first one, and you should consider planar distance match some target phase. For example, if you got one diffraction, for example, like A, like in this image, you got one diffraction A. There are many spots. So you can measure the distance between the reflection spot to the transmission spot. Then calculate, the distance of of this spot. Then this corresponding to the plane distance. Then you should have some target phase. Then you can match which plane does this one match here. So another thing you need to you need to pay attention in the lattice extinction rules. This is important. Today I would like to highlight this one. So what is the meaning of the lattice extinction rules? For example, we can still maybe we can look for the pattern E. In this image, look for E. Index 002. No, 004 pattern. There is no 002, no 001, no 003. So if, for example, if you find that 004 maybe match some patterns, some plane distance, but you find some additional spot, they should not occur, but they occur. That is wrong. That's meaning your index is wrong. And the third one you need to pay attention is index plane must within a room axis of diffraction must meet this rule. For example, HU, I mean multiply U plus K multiply V and LW, this should be 0. For example, I mean in this image, you can pick up anyone, like for example, like F. So I index 004. If you multiply 004, 110, it's 0. So sometimes you may see in the literature, they index some lattice, some spot, I mean some lattice plane, and also some room axis, but actually they are wrong, because if you multiply them, they are not 0. That means wrong. And another one you need to consider is the intersection angles between two planes within an individual zone axis. What does this mean? You can see F. In the image, see F. I indicate two spots. H1, H1, K1, L1, H2, K2, L2. You know, these are two planes. So what you need to do is for example, sometimes when you do is you can find for example, you can find you know, the H1, K1, L1. You know, this spot, you know, the distance can match with many lattice planes, and this H2, K2, L2 also can match many planes. Then to choose which one, they must meet this you know, they must meet. For example, you can calculate this angle based on your target face. Then you can measure this angle, make sure these two equal or similar. This is one thing. Another thing you need to pay attention is intersection angle between two zone axes must match. For example, and you can see in F and E, you know, when you take the electron diffraction data, you know, for example, take the data E on the microscope software, you can find the tilting angle X1, tilting angle Y1. Then when you take the diffraction data F, you can find the tilting angle X2, Y2. Then you can use the formula, for example, like cosine theta equal cosine X1. I mean, this tilting angle difference, X difference, Y difference, they can get this theta. This theta meaning the experimental angle between these two zone axes. This one must match with for example, your target face. For example, for your target face, if you index this is 110, if you index another one is 210, you know, their angle is different different from your experimental observation. That means it's wrong. So that means when you index the diffraction patterns, when you index, you know, the structure, usually you should consider many things. That's why you know, this is I'm doing it. That's why I do this. You know, it's a serial. You know, I mean, large tilting techniques I use. You know, I tilt my green at many angles. Then I got many diffractions. Then I verify all of them match perfectly. Then I can use this way to identify, you know, the space group FDD lattice parameters. Of course, I mean, for your own project, before you do the diffraction, you may already know what is the phase you have. So that's why you don't need to do, you know, so many things as I do this large tilting. But if it is unknown phase, you have to do like this. Okay, so now today, I will focus on the lattice extension rule. This is very important. So many times, I mean, it's very easy to ignore this. So that's why I want to pay attention to this one. So first, let me give you some introduction about lattice and space group and point group and space group. You know, for a solid state matter, you usually have three state. One is a crystal structure. This one have a translational period. Another one is query crystal structure. This one has no translation period. And another one is amorphous. This one only have a shortened ordering. So if you divided them, you know, for today we only focus on, you know, the crystal. We do not I do not talk about the space group for query crystal. That is more complicated. For the crystal structure, there are usually 7 lattice. I mean, for example, there are 7 crystal classes like a cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, trigonal. And for each class, you know, they have ABC, alpha, beta, gamma. ABC is, you know, the lattice parameter, the distance ABC, and alpha, beta, gamma is 3 angles. They must have this feature. For example, for a cubic, A equal B equal C, alpha equal beta equal gamma must equal 90 degrees. And for a monoclinic, you know, A should not be, I mean, A, B, C should not be equal. and beta should not be 120, and alpha gamma should be 90. You know, if you use this 120, it should be it may be a hexagonal. You know, there has all of them lattice have their own features. You should know this. Another one, there are 4 types of unit cells. For example, P indicates a primitive one. For example, like the cubic, P is a primitive one, and I is a body centered. You know, in the center of the cubic, you see one spot, one atoms, and F is a face centered. Every face have one. I mean, in the center of the face have one atoms. And then another one is a C side. Is a C we usually use site centered. For example, like orthorhombic, you know, there are only one face have this atoms. So if you combine this, you know, 4 types of unit cells and 7 crystal classes, you got 14 Bravis lattice. And now, I mean, let's move on. I will show you some symmetry operations in Swiss group for crystallography. So there are some we call microscopic symmetry. All this microscopic symmetry has no translational feature. For example, you know, there are L1, you mean only L1 actually meaning no symmetry. I mean, it's no rotation. I mean, it's no symmetry. L2 meaning 2 rotation row axis. Meaning, for example, rotation 180, you got another same point. Now there is a rotation 3-fold rotation row axis, 4-fold, 6-fold. Actually, if you see the B, you know, there is some define for the rotation symmetry. For example, if you rotate from x, y, z to x prime, y prime, z prime, I mean, z should be same. You know, if you rotate this angle, 2 pi divided by n, you know, if 6, you will rotate 60 degrees, you got a same one. This is a rotation. We call a rotation row axis. Remember, there are only 5 rotation row axes in the crystal. No 5-fold, no 7-fold, no 8-fold, only this 5-fold. Because only this 5-fold, you know, you can pack in the full space. And another one is a reflection. The reflection one, you can see this one is in D. In D, you know, x, y, z. Reflection with xy plane got another one, xy minus z. This is a reflection. And then another one is inversion. Inversion, you can see A. Inversion basically from xyz to minus x minus y minus z. In the crystallography, you will only see this type of, you know, basic operations. Of course, there are some combined operations like we call, I mean, obviously we should call them roto inversion. They basically mean rotation plus inversion. This means, for example, on your 6-fold, 4-fold, I mean, row axis, you can add inversion, meaning that, for example, so you can do like a C, this image like C. You see that first, you know, this is a 2 operation. First, x, y, z. You apply rotation, it go to x prime, y prime, z. Then it do a inversion. Then got a minus x prime, minus y prime, minus z. So this we call a n-fold roto inversion row axis. You know, all this one, you know, the basic one and the combined one, they all this belong to the microscopic symmetry. This one never contain any translational feature. But there is another one, you know, another one we call a microscopic. You know, it's a combined operation, combined with a microscopic symmetry plus partial glide, partial translation. Because, for example, if the lattice is A, if you translate A, then it means it's a full translation, it's a full glide. That's not it must be a partial glide. For example, we have some. If we use this reflection and partial translation, we combine together, we got the glide reflection. This means we have A glide plane, B glide plane, C glide plane, N glide plane, D glide plane. Only these 5. I will show you later more details for the glide plane. And also there, if you combine the partial translation with the rotation axis, you got a screw rotation axis. For example, the screw axis can be 2, 1, meaning your rotation 90 degree, then plus, for example, 0.5 C translation. And if you 3, 1, meaning your rotation 120 degree, and then translate with 0.333 translation, partial translation. For 7 means your rotation 90 degree, then plus 0.25 partial translation. I will show you later. For example, in this one, I will show you the more detailed. What is meaning for I give you some schematic of glide reflection operation. For example, you have what's this? Rabbit, maybe here. So you do a reflection, you got the bottom one. Then this is reflection. But if you do another partial translation, you got here, this one. So let me how to do some label. So from here to here, this is we can call a glide reflection. Then if you do another glide reflection, it will come back here. This is 1 to glide reflection to 2. Do it again, go back to 3. So this we call the glide reflection. And there are many types of glide reflection. I'll give you at least a table here. So for the glide plane, it's a combination of reflection and translation. The translation must be parallel to the reflection plane. And the translation component can be half of the translation unit or quarter. But they should always parallel to the plane. For example, there are many translation planes like ABC. ABC basically is we call a axial glide plane. For example, there is some label. Now, if your plane, is normal to the plane of projection, this is some international standard label like this. It's a glide plane, C glide plane like this. And if your plane, is parallel to a plane of projection, you should label like this. Basically, wait, let me, how to make a label. So, for example, this one and this one actually the same. They represent the AB glide plane, but they just you see this glide plane operation along different projection. So if for the AB glide plane, the nature of the glide translation is like this: 0.5A, 0.5 or 0.5B. And for N glide, they can label you this one. The N glide we call the diagonal glide. So the translation of the nature of the translation should be, along the diagonal direction about, A plus B divided by 2. So if it is a D glide plane, D glide plane will usually call a diamond glide plane. And they have, based on, your operation direction, there are usually different labels like this. Basically, all of these two represent the D glide, but just you observe direction is different. And for this one, the translation is a quarter of A plus B. Okay. So now I briefly introduce you the glide plane and their symbols. Now let's move on. I will give you show you more detail. For example, first I will show you some schematic of the screw axis rotation. For example, 6-1, use rotation 60 degree. For example, rotation 60 degree, then have a 1 in 6 translation along this axis. For 3-1, use rotation 120 degree, then you have to translation, 1 in 3 translation, like along this direction. So this table show you the label for 2 axis, 2-1, 3-3-1, 3-2. This all of them are standard standard symbols in the international label. That's why when you read the tables, international space group table, you should understand the meaning of this basic operation. Okay, so previously I showed you that we have 7 crystal class. If you plus the translation and centering, you will got 14 Bravis lattice. And if you only, for example, apply the rotation, apply the operation, like rotation, reflection, inversion, without a translation, you got a 32 point group. This point group is actually a plane group. Not 3D, it's 2D. That's why usually if you want to describe the symmetry of some molecule, then you use a point group. But for a solid state materials, for example, you will usually describe them using a space group. Space group basically you based on this two, you add them together, you got 230 space group. So the space group, contain all the information in 3D. Okay, now I want to show you how to label, this operation elements. For example, their mathematical descriptions. Like the x prime, y prime is our post operation. X, y, z is original. Oh, sorry, I missed them. Is the original operation. Then T is a translation vector. You can describe this using this kind of mathematical way. For example, for 6-1 row axis, the operation matrix is here. You can, for example, you can use this one to calculate. If you give original coordination of your atom, you will got another one. Then for unglide plane, the plane is on this plane on 1, 0, you can use the operation matrix is here. So for example, we can for twofold, this is a matrix, twofold rotation axis. The twofold rotation axis may be on different direction. If 1, 0, 0 like this, 0, 1, 0 should read like this. So for the operation operated by two continuous, for example, twofold rotation, if you apply a rotation twice on an original position, this rotation along different, this is wrong, this is 1, 0, along different direction, you can multiply them, you got this one. This is actually another 2 rotation axis, but along 0, 0, 1 direction. This means if you combine 2 or 3 basic operations, then you got another symmetry. That means although you have 3, but some of them may be not fundamental or not basic or not dependent. Okay, now let's move on. In this slide, I will show you, basically I quickly show you, how, the symmetry, the operation elements and their location of the symmetry for the point group. There are 35 point group. The point group, we didn't consider translation. All of them is shown here. And so this table, for example, show you a more detailed, like you know, the symbol, or you know, our crystal class, and in each class, for example, how many point group they have, and how many space group they have, and what is their feature. For example, for hexagonal, you know, there are 4 points group, 5 space groups, and this is the relative features. Okay, so next one, now let's move on. I would like to show you the contribution of the diffraction intensity from a unit cell. You know, for any solid material, they have a unit cell. I mean, crystal, they have a unit cell. And the scattering amplitude can be described using this one. And this F theta, you know, is an atomic scattering factor. And this, I mean, this one is described as a scatter wave. So this Ri is a vector defining the location of each atomer, meaning your location of the atomer in a unit cell. And this K is a diffraction vector of a unit. This K here equal G. You mean when you index the diffraction, you use G, the plane. So now you got something like this. You can got like this. If you put them together, then we have this one. We define this one. This one we call the structural factor of a unit cell. This determines the intensity of a diffraction pattern for each reflection, because you know the square of this one, I mean, it's proportional to the intensity. You know, like that. So that's why is you know, the intensity of your reflection in your diffraction pattern actually related to the atomic location and also the symmetry of your unit cell. Let's give you more examples. For example, example 1 for FCC lattice, you know, we have this structure factor, and for the FCC lattice, the atom, the location like this, 0, 0, 0, 0, 0.5. This only have 4 atoms, and then we put them together, we got this one. And for this one, you know, for this I do some for calculation like this. You know, E theta I equals cosine theta and plus I sine theta. E pi I equals -1. E 2 pi I equals 1. So if we put this location here, we got this one. So if HKL are all even or odd numbers, then this FKL structure factor is 4F. This is F is atoms, I mean scatter factor of each atoms. For this FCC, we suppose all of them are the same, so that's why we got this one. But if HKL is mixed number, some even, some odd, then all this number will be 0. That's why for FCC lattice, only the HKL plane, all of them must be even or odd number. You can see for all the others, it's wrong. For example, if you index the FCC structure diffraction, if you got a 1, 0, 0 plane, it's wrong. You got a 1, 1, 0 wrong. You must go to 2, 2, 0 can occur. So this is something we can got. Now let me give you another example. So how to use this one? You can check the international table actually. For FCC lattice, the HKL plane existing rule is must be even odd number. You can check it. For the FCC, the space group is 2, 2, 5. And you can see here, there are in the table, you see there are 4 atoms. And if the original location is from 0, you know, you can see here. And if you check here, the reflection conditions, you will find this. Basically, this is the same as I show you. HKL must be all equal or all even, all odd or even numbers. Okay. Now I would like to give you another example for ordered FCC. Ordered FCC, for example, like this. For example, the beta nickel aluminum. The aluminum is in the you know, in here. the nickel is in the side center. Then the aluminum, the location 000, one location, and the nickel is 3 location, like this. If you put them together, you got this. This is a structure factor for the ordered FCC. For example, for this one, if HKL are all even odd numbers, you got this. FKL equal to F aluminum and 3 plus 3 F nickel. F aluminum, this is a scattering factor of aluminum. This is a constant. You can check the number of, from a table. And if they are mixed numbers, FKL equal aluminum, F aluminum minus F nickel. This one is in some diffraction pattern. You may see some reflection are very strong intensity. Some of them are weak because they have a different structure factor. Okay, then I give you an example. You can also see this. For example, if it's ordered, FL1, LN2 type, it's a space group is 221. And if you check the table, you see here, all of them can occur. There is no extinction because of order. Now I give you another one for the B2 type ordering. The B2 type, so this is B2 type is beta nickel aluminum one. So this is only 2 atomers. One is aluminum 000, one is nickel 0.5, 0.5. If you put them together in the structure factor, then you got this one. If H, K, L, they are, you plus them together. If they are even numbers, you got FKL is aluminum plus, scattering factor plus nickel scattering factor. Got this. But if they are odd numbers, you got this. They are difference. They are minus. That's why is for the ordered B2 structure, you see some different patterns are very strong intensity. Some are weak. Now, for example, if you for the B2 type, you check the table, you also found there are no extinction. And I will give you some examples. For example, this is a diffraction is for the FCC. You see 000, 111, 002. You do not see 001. You do not see 01 this. And for the FC, for the L12, you ordered one, you see some weak spot here. Weak spot here. And if you got a B2 structure, you will for the B2 structure, it's another one. B2 structure, this is the ordered one. You can see all of them, but they are still weak. So see. And now I will show you how to read and use the space table. For example, I'll give you some example. Like the space group number 127, this is some Hobbic one. This is official label. Is like this. And this is space group number. This is D4. This is D4H5. This is a show file or Schoenfeld notation. This is there are different kind of notation in 3D. And you can also see this one. This one is a full number, a full label of the table in the space group. This one is label use human HM notation. This is actually a point group. You mean remove all the translation feature. Then you got this one. This is crystal system, trigonal. And this one also, this one is symmetry of the Peterson function. Then when you do the XRD quantification, then you will need this one. And then this one show you the location of every symmetry elements. And this one show you a set of equivalent point in a general position. Okay, then I will give you a table. For example, the general catalogs and the feature of different crystal structure. Some of them have a low symmetry, some are middle symmetry, high symmetry. For low symmetry, they only have one. They have different kind of. Oh, this should be a 2 minus inversion zone axis. So this is for symmetry elements in the point group, and also the symmetry of each lattice. For example, for a cubic one, you may see a space group. They have there are three major directions: 0, 1, 1, 1, 1, 0. To describe a trigonal, for example, a space group, you for example, for a space group, you already see 3, 1, 4, M, B, M. So these 3 indicators different directions. Then for this one is a tetragonal. For tetragonal one, you know, the first position, tetragonal is here, indicated a symmetry along 1, 1, 0, 0, 1 direction. Second one, 1, 0, 0. Third one, 1, 1, 0. You know, this one I show you, you know, more detail. You know, this one is a P indicator. I give you a space group, you know, like the P primitive lattice. For M, you know, this is indicator the first direction, second direction, third direction. And the first direction for tetragonal one indicated 0, 1, 0, 1 direction. That means along this direction you have a fourfold axis, and also you have a reflection perpendicular to this. And the second one in the third direction, you have a twofold screw rotation. You have a B glide plane. And the third direction, this one along a 1, 1, 0 direction, you have a 1, 1, 0 rotation rule, and also M reflection. So you can use, you know, for the fourfold rotation, we have this one. For the twofold rotation, you have this one. You know, for the big glide rotation, you can go to this one. So if you combine some rotation, some symmetry together, you will find, you will generate some new row axis, some new symmetry. They are not independent. That's why in the table, you usually see a simplified table, another a full, simplified symbol, also a full symbol. Also, okay, now I give you another example. For example, how to get for the FCC lattice. For example, I give you an example for, more complicated one. This is a tetragonal, this one. This one, the number is here. And we calculated the F, the structural factor. And we calculated the most general one, location. This means the most general location. If X equals 0 or Y equals 0, Z equals 0, you got some special location. That's why you find many like a Y-curve location, different Y-curve location. They have different. So for the most general one, we calculated this F, and through many long formula, long calculation, you can read this in detail later. Then if we move forward, you will got this one. Finally, you got this one. And let us consider the crystal quantum plane. For example, for this HKL, in some special case, if HKL equals 0, then for example, the type of H0, 0, you got this one. This one, if H even number, F 0, that means if you let it for this space group, if your plane you have this form, H00 form, if H is even number, F is 0. And for the HKL with some special cases, for example, H, if you have a 0 to KL form, then you also have some cases this is 0. That's why, for example, you got it here. If your lattice index at lattice have a 0 KL form, if the K must be even numbered. If for the HLL form, L must be even numbered. All of them, can be calculated by using this way. And that's why, for this one, this space group, we got this one. And if you add if you calculate at some special location position with x, y, z equals 0, this you can simplify this. Then you got this one. That's why in an international table you will see this is a reflection condition for the general location. This is for some special location. So I do another. Then I do. So actually, this for the 0 KL type, this is related to the reflection rule resulting from a big light plane. And for this H00 type, they actually extinction rule related to the screw axis. So that's why it's only the partial lattice translation, like FCC centered, BCC centered, side centered lattice, and symmetry having partial translation can cause lattice extension. For all the other, there is no lattice extension. So this is another one. So this is we do another calculation for some for a real phase like this boride, and you find the atomic location. You put them together in a structure factor. Then you can do some calculations. Finally, you arrived like this. You arrived here. Here, I mean, you can read in detail when you go back. So here, then you can analyze through this. You can go this one. Meaning is that the F, finally, this boride equal this. So equal this. So if for H even number F0, so if your HKO have this type, then you got this one. This means for different type of the lattice plane, they have different extinction rules. And this one I will show you. For example, this is a real example for this boride. For this boride, if you have a HKL, if with special case H for HKL is equal 0, for example, if for H00, H must be odd number. For example, H00, the H0, for example, the 020 can occur, 010 cannot occur, but they occur. This is actually related to the dynamic diffraction, because, for example, so for this 110 can occur in our diffraction. This 120 can occur in our diffraction. Then if you consider dynamic effect, this 010 will occur. So that means although there are lattice extinction, but they can still occur due to the dynamic effect. And finally, I give you a long table. So in this table, you will find a detail for each symmetry. Will they cause any lattice extinction or not? For example, for 3132, for a lattice, if your lattice have a 00L form, L must equal 3n, then it can occur. And for 6165, I mean 00L, L must be 6n. Only this can occur. So for microscopic symmetry operation, they always have many different kind of rotation rules. Okay, so I want to stop here. So if you have any question, please let me know. We can discuss. Thank you.